Hey, this is Mr. Resentis again. Chapter 4 this time. I'm on page 120. This is section 1, changes in motion. Alright, so this chapter what we're going to talk about are forces. And I invite you to read the chapter. I'm going to try and summarize some of the highlights here. Alright, so what we want to talk about is how force affects the motion of an object. We want to look at that very carefully. When you make contact with something, chances are you're applying a force. So if you so force can cause change in motion. So, consequently, interactions between objects and their environment are caused by force. There's different types of forces. There's contact forces, and there are field forces that your book refers to as field forces, or what I learned as non-contact. And these the contact forces are friction. Friction is a force. Air resistance. That's a force. You can apply a force. Applied force, I'm applying a force, or a normal force. The normal force is the force that's pushing back on the rubber eraser as gravity's pushing it down. So gravity's pushing it down, and the normal force is holding it back up. That's why it's not moving. So the normal force is what's preventing it from moving, because something is pushing it from underneath. Gravity is a force. It's a non-contact force, and then you could also have magnetic and electrical are also considered non-contact force. We'll get to those. We'll get to those later. The unit for forces are newtons. And a newton is the amount of force when acted on a 1 kilogram mass produces an acceleration of 1 meter per second squared. So 1 newton equals 1 kilogram times 1 meter per second squared. So what we could do is we could calculate the force of gravity. Alright, because the force of gravity equals the mass times the gravitational force. So a typical 80 kilogram person times 9.8 newtons per kilogram, which is applied by by gravity, equals 784 newtons. So that's how much force is being applied by a typical 80 kilogram person. 80 kilogram person might weigh about 180 pounds. So to draw a force diagram, you would have in equal opposite forces. You have 784 Newton force that's pushing down because of gravity. And then you have 784 newtons pushing back up, and that's called the normal force. As you walk, or as you're standing somewhere. So the normal force is being applied by the earth or by the ground or by the floor, and then the gravity is, of course, is caused by mass. And we'll talk more about where the gravitational force comes from. So if we did practice problem A on page 124, number 2, all you're supposed to do is draw this force diagram of a physics book. Alright, so here we have our physics book, and we have a force diagram. We have a normal force being applied, and we have a gravitational force being applied. Here's gravity, and here's the normal force. Just pay attention that these two force vectors should be the same. This should be the exact same, okay? In magnitude, in size, all right? And otherwise, it'd be moving. I mean, if this one was greater, it would be moving up. If this one was less than that, it would be moving up. But that's how you draw. That's just basically how you draw a force diagram. All right? Now, Newton's first law. It's the law of inertia. A body will remain in motion or rest. We mostly focus on rest, but it will remain in motion unless it experiences a force. All right? So a meteor will just keep traveling until it experiences another force. So this, of course, this force vector is a lot greater, so this is moving in this direction. The sum of the forces acting on an object is called the net force. So the net force, of course, in this case would be this direction. All right? So we could also show you another force diagram. Here's another force diagram. The yellow, of course, is the biggest of the force, and so this car is obviously moving in this direction because the driving force or applied force is greatest. The force of gravity is holding it down. You would also have friction, which is the red arrows; those are less. And then what's called the reaction force here, I call the normal force that's keeping it on the ground. So it's the ground pushing back up on the car. And then this force would be air resistance. And so the reason why the car doesn't just keep going and going and going is because it keeps running into air resistance, and it has friction. Or if it didn't have these two, it would just keep rolling and rolling and rolling. All right, so we have another practice problem, and this is practice problem B. And practice problem B is on 128, I believe. In this case, we have an apple. So here's our apple, and the apple is falling with a force. I believe it's falling with a force of 2.25 newtons. But there's a wind blowing, and the wind resistance is 1.05 newtons in this direction. And so what we want to do is find the net. Oops, my apologies. Find the net. Find the net force. Well, in this case, what we have to do is we have to find the resultant. Alright, and so what I'm going to do is just basically move this vector down here. I'm going to move this vector down here, and I'm going to find the resultant. And in order to do that, well, I could just use Pythagorean. So all I have to do is 2.25 squared plus 1.05 squared equals d squared, so 2.47, and those are in newtons. I should is d. Now I should get the angle as well, the angle of that net force. And in order to get that angle of that net force, this angle here, I would take the arctangent multiplied by the arctangent of opposite divided by adjacent. All right, so the arctangent of opposite and adjacent. Okay, and that would be 105 225, and that equals 25 degrees is our angle. So that's practice problem 2. Lovely.